Okay. So welcome back to lecture 2. Okay, so remember where we were? We're going to be studying the optimal linear regulator, but we're going to do it undergraduate style. So we're going to study the undiscounted problem, or there's a minus sign in front. We're going to put a sequence of Lagrange multipliers on our constraints. I'm going to put a 2 here. You'll see why, because I'm using quadratic forms. And that's the multiplier on the time t constraint. So let's get our first order conditions. With respect to ut xt plus 1, what they're going to be is two q. We'll use a linear algebra again. There's a Lagrange multiplier. That's going to be for all t greater than or equal to 0. Then we're going to have we just got those by taking derivatives. This is going to be for t greater than or equal to 1. And we're going to define mu 0 to be a vector of shadow prices of x0. And we're going to apply the envelope theorem to call this star now to get this condition at t equals 0. Okay. Now, if you study earlier in the chapter, there's a section. Again, I'm talking about chapter 5. It's section 5.4, and it's entitled Shadow Prices in the linear regulator. And a very simple argument is gone through at that time to deduce a conclusion that we're going to use here. And it is that it's that mu t, that shadow price, is related to the p in the value function that we derived last time by this equation. So, and furthermore, that's identifying pt, mu t, as the gradient, well actually 2 mu t is the gradient of the value function. And I want you to go through that argument by yourselves. Okay, so there's going to be, just in the background, remember that these mu t's are related to P, even though we haven't explicitly brought them up yet when we wrote this problem. And this fact was an insight. I think one of the first people to do this was Vaughan, when he in the 60s or 70s, when he devised a fast algorithm for solving Riccati equations. So we're gonna sort of follow in his footsteps today. Okay, so here's what we're gonna do. We're gonna take this system right here, and we're going to be working with this system. And what we're going to do is we're going to go through these steps. We're going to solve for ut as a function of ut plus 1. That's going to be our strategy. And substitute into the law of motion and we're going to stare and rearrange. And we're going to get a beautiful system. We're going to get this system. It's going to be a first order system. And remember, each of these x is an n by 1 vector. So that means mu t, the shadow prices, are also an n by 1 vector. We're going to get this system. And in particular, this L matrix, this is just simple algebra, little linear algebra. Turns out to be this. In some literature, these are kind of famous equations, but looks like this. And xt, that's our state, and mu t is often called the costate. Okay. So when L has full rank, it's invertible, we can write this system, and we're going to assume we can do this. And if you just do a linear algebra, this M, that's that. It has this form. There's no reason to memorize this, but we might as well write it down. B prime A prime inverse R. So we're going to have this partition matrix minus A prime inverse R, and then here we're going to have minus B Q inverse B prime A prime inverse, and we're going to have A prime inverse. That's our matrix. This matrix M. And so here's what we want. I keep using the equation. I'm going to call this star again. I'm recycling star. So here's what we want. We want to solve the difference equation system for a sequence xt. That's actually what we're after. I'm going to start from 0 that satisfies our initial condition whatever is given. And, okay, now remember our little lecture on stability? And we want limit as t goes to infinity of xt to be 0. We're going to impose stability. This is the counterpart of a transversality condition. The logic that we use to get it is the stability argument we went through in the last lecture. Okay, so that's what we want. And let's see how we're going to get it. So now I want you to look at the lecture, and I'm going to sort of guide you through this. There's some magic properties. So we're going to stare at M. Here's the way this is going to go. And we're going to use some linear algebra. Okay. So I'm going to introduce this matrix J. And this is going to have the following property. By the way, John Muth knew what we're talking about, even though he did not use this mathematics. It's remarkable. So there's my matrix where IN is the n by 1. That's the n by 1 identity matrix. That's what that is. Okay, so here's going to be a definition. So you can check the rank of J is 2n. You can check that. So here's going to be a definition. A matrix M is called symplectic. Symplectic. If following is true, M, J, M prime equals J. That's just a definition. And fact, the matrix M defined in is symplectic. That's just a fact. And how do you prove that? Just multiply it out. Just verify this equation. That's how you do that. Okay. Well, that just seems like language. But now here's the killer fact. I'll call this killer fact. The eigenvalues of a symplectic matrix occur in reciprocal pairs. And what that means is, that i.e., if lambda is an eigenvalue, so is lambda inverse. Consequence, roughly. half the eigenvalues of M are, I'll call them stable, meaning lambda less than 1, and half are unstable, meaning absolute value of lambda is strictly greater than 1, which means that these contribute unstable, explosive dynamics to both xt and ut, and threaten to send, and they don't threaten, they send, and they send xt absolute value to plus infinity, and they send ut to plus infinity. So this looks bad. This looks horrible. This looks bad for us. And this used to be called, this actually had a name. It's so bad, it used to be called the Hahn problem. Frank Hahn, the great British economist, viewed this as a problem in the economic dynamics. Because we want, remember, I want a solution of the, see, this system here is just our first order conditions. We've just rearranged all the first order necessary conditions. Star is just the first order necessary conditions for our dynamic system. And we want to solve it for an optimum. But in our strategy, we told you what the strategy, what we want to solve the difference equation star for a sequence that satisfies x0 and that's stable. But the fact that the matrix M is symplectic and that its eigenvalues split equally between positive and between values strictly greater than 1 and strictly next than 1 means that almost all of the solutions of that equation are unstable. So we want xt to be going to 0, but almost all the solutions of that, now I say almost all solutions violate this. So almost all leaves a little bit of hope. So the beautiful thing is it's going to turn out there exists a unique solution that doesn't, in which xt and mu t both go to 0, 0. It's a unique solution. And this is the one we want. And to find it, we have to disable, we have to disarm. We have to disarm the unstable dynamics. And now how are we going to do that? How are we going to do that? This is the logic of the problem. So let's go look at our system again. I'll copy the system down again. This beautiful system. And now let's stare at this system. This is true for t greater than or equal to 0. And we have one initial condition. We have x0 equals x0 bar given. Now we stare at this, and one thing we might ask is, wait a minute. The first order difference equation, there's the dimension of xt ut is 2n by 1, we only have n initial conditions. What about mu 0? So mu 0 is free. We have to determine it. I'll just say we get to choose it. Okay, so we want to choose it, if possible, in a way that disarms the unstable eigenvalues. That's what we wanted to do. So the question is, can that be done? So the phrase is, seek and you shall find if you don't seek for too much. So the answer, the remarkable answer is, setting mu 0 equal to p x 0 disarms the unstable dynamics, where P solves the algebraic matrix Riccati equation. That's our punchline. So in this system here, the way this is x0 is a state variable. And the way some people, like Nancy Stokey, might say this, mu 0 is a so-called jump variable. We must choose it. And the way we choose it is to enforce the key condition that we want a stable system, because an optimum path is going to be stable because of the stability argument we gave. And then I'm asserting that this is the way to choose it. And then once we do that, it's going to turn out, if we set mu 0 equal to p x 0, it turns out that system star will imply a couple nice things. It'll imply that xt goes to 0 as we want, and it will also imply that mu t is always just pxt. So those are nice properties. Now, what's our proof strategy going to be? So the proof is in chapter 5, and the best way for you to digest the proof is just to study it at your leisure. I'll just sketch this and show how it's going to go. The key weapon is going to be something called assure, S-C-H-U-R, decomposition of M. And you can look up what assure decomposition is in Wikipedia or MATLAB or Python. MATLAB and Python have nice programs that implement this. Okay, so here's what we're going to do. Here's a quick sketch. We're going to I'm going to go quickly over this because I want you to study this on your own. We're going to rewrite star as this, where in an obvious notation we're going to stack. We're going to see this later. We're going to stack this to be xt mu t. So we're going to see this in the next lecture too, this little trick. So we have this system, and now we're going to consider the following triangularization. We're going to triangularize. This is going to be the shear decomposition. There's going to exist a matrix V that has the property that V is going to triangularize. This is our secret weapon. Every block is n by n. It's triangular. That's a matrix of zeros. And the key thing is W11 is going to be a stable matrix, and W22 is going to be an unstable matrix. And by that I mean all the eigenvalues are less than 1 in modulus, absolute value, and all the values are greater than 1. And what this triangularization does is it sorts the eigenvalues into parts that are stable and unstable. So now what we're going to do is we're going to solve the difference equation star using this triangularization. And what we get is the following. We get yt, just do some linear algebra, we get the following. Yt is equal to w1 raised to the t. A matrix w1, 2t, I'm not going to give you the formula for it. It's in the text. And this matrix w22 raised to the t, the inverse, y0. That's what this does. Now we stare at this baby. And actually, here's a common trick. We're gonna just to make things more transparent, I'm gonna define yt star equals v inverse yt. And that's gonna make the dynamics. So yt star is just a linear combination of the yt's, where the linear combination is determined by the inverse of v. So now what I'm going to do is I'm going to write this system like this. This is a system that and okay, so now I'm going to write this system like this. y1t star, y2t star. That looks like this. And now we're just going to stare. That's raised to the t. We're just going to stare at this. Actually, when you're proving theorems or trying to understand something, you do a lot of staring. Cup of coffee, walk around. This is one of these coffee things. So you have this thing, you say, okay, I did some work. I did this symplectic thing. What did I do? M, shear decomposition. I just did two things. And then I got this. Now I stare at this. Okay, this matrix, all of its eigenvalues are converging, are strictly less than 1. So this is a matrix of stuff converging to 0. This is a nice bounded matrix. Well, this matrix isn't going to cause us any trouble. This is a matrix where we have components converging, all the components are converging to, in absolute value, they're converging to plus infinity. They're blowing up. Fine. But if we look at the y12, y2t component, it seems to depend on both the component that's blowing up and the component that's not blowing up, unless we disable these dynamics. So how do we disable these dynamics? we've got to zero this out. We've got to zero this out. So essentially what we want to do, we want to silence the Y2 star dynamics. So how are we going to do that? How are we going to do that? Well, I'm going to write down the formula for Y2T star. And I want to zero it out for everything. So V21 is the 2-1 component of the inverse of V21 is, I'm going to partition V inverse. I'm going to partition V inverse. And this is going to be the 2-1 component of it. So if you look at our definition, V Y2T star is going to be that. If we just go back and look at the definition of Y2, where we defined, oh yeah, it's right here. So I'm going to take V inverse and I'm going to partition it into V 1 1, V 1 2, V 2 1, V 2 2. I just do that, and then you'll notice I'm just reading right off of this the definition of Y2 star, and I want to. What do I want to do? I want to set it to 0. I want to set that equal to 0. So to set that equal to 0, I'm going to set mu 0. I want this for all t. I'm going to set mu 0 equal to, well, minus V22 inverse V21 times x0. This is going to, and that's going to also, you can check it out, that's going to imply this. But this works. This stabilizes, and it disables the unstable dynamics. And now some magic has occurred, because I told you earlier that it's going to turn out that that mu 0 is P x0. So it's going to turn out that P is equal to minus V22 inverse V21. And this is a formula. This uses the Schur decomposition to compute P in the value function without, I'm going to put this in quote, without solving the Bellman equation So that's it. That's the whole story. This is how we solve the problem using a Lagrangian, and being very careful about the stability requirements that we need. So a little history of thought. This turns out to be, this is a fast way of computing P. It's much faster than iterating on the Bellman equation. So this is widely used in industry, or versions used based on this. And this is also similar ideas are used to solve linear rational expectations models, in which half the eigenvalues, I'm going to write this, satisfy lambda strictly less than 1 over root beta, and half are explosive. And I've adjusted this condition for discounting. That's what the condition is. So, for example, Dynair and Sims's GenSys use such an algorithm. And it's all based on the Shor decomposition. They're all based on the Shor decomposition, or something equivalent. Okay. So these ideas are very powerful, and we're going to use them in the next lecture. We're going to see them in the next lecture when we come to studying for the first time in this course representations of time inconsistent optimal plans. And you know what's going to surface when we do that, the same ideas are going to come back. There's going to be something, the thing to watch for is watch for the counterpart of setting Lagrange multiplier, also known as costate variable, also known as a jump variable, at time 0 in a special way. That's one thing we're going to have to watch for. So the ideas that we talked about are going to come back and make an appearance in another context where we might not expect them. Then I want to just conclude this little lecture by coming back and talking about the Kalman filter. So here's what I want you to do. I want you to rewrite the equations for P, J, and Fj. So I'll leave some space to rewrite them here and here. Because last time I asked him if they reminded you of anything, and then I'll come back to that in a minute. So here's from last year with Tim Cogley. Here's his beloved state space representation, where here's one popular way to do this. The state space, Wt plus 1, everything in sight's a vector. This is normal 0i. Vt is normal 0r. That's a covariance matrix. This is a state. It's hidden. These are observed, called the so-called observer equation. So this is an example of a linear Gaussian hidden Markov model. So you could check this. Xt is a Markov process. Check the conditions. YT is not Markov. So this is called a state space representation. So here's what we want. We want, for a variety of reasons, we're going to define a history of observations. What is observed at time t is a history yt back to y0. That's what's observed at time t. And what we want is to compute x hat t plus 1, which is the conditional expectation of xt plus 1 conditioned on yt. And, to complete this system, if we just wrote this down, Cogley would get really upset over this. There's an initial condition which is also unobserved, but it has initial mean x0 hat, and it has initial covariance x0, sigma 0. So this is how we initiate this system. So now we filled in an initial condition, and this system runs for t greater than or equal to 0. So this is the Kalman filtering problem. This is what we want, where that's the history. And the answer to this is something called the innovations representation. And beloved to Cogley and all applied time series econometricians and people who work on, like Chris Niemark at Cornell, who work on models with higher order beliefs. This is a recursive formula starting with x0 hat given. It's a recursive formula for this object, and the formulas are the famous formula for the Kalman gain. And the famous formula for the law of motion of the state covariance matrix. The formula where sigma t, very useful. It's the covariance of xt, the covariance matrix of xt around its best estimate. So Cogley derived that, and the way you derive it is you run a regression. You run population regressions. Cogley probably said you use Bayes' law. In this context, that means run regressions. So there's our answer. Now, what I asked you is before, do these two equations, well, now I'll ask you, do these two equations here remind you of anything you saw in last time's lecture? And then the other thing is, are they the same as what you saw in last time's lecture? And I hinted before that the answer to the first question is yes, and the answer to the second question is no. So let's fill in what we got last time. We would have gotten this equation. And we would have gotten this equation. Here we go. Bear with me. I have a confession. I took a class when I was a professor at Minnesota in the math department, and I was told I should memorize these equations and never forget them. I never succeeded in memorizing, so I have to copy them. Okay, so here's our Riccati equation. It's a Riccati difference equation. And we solve this starting from j equals 0, and we go 1, 2, 3, 4. And this is backwards induction from the Bellman equation. Those are two equations. So if we compare these equations to these equations, and it had been a while, you might say they're similar. They were there, you might say they're the same. But so look at this one. There's a matrix of this structure, and it's inverted, and it's pre-multiplying something. Well, there's that matrix, it's inverted, and it's post-multiplying something. What it's post-multiplying might remind you of this, but it's not the same. This equation is going backwards in time. This equation is going forwards in time, but it has a structure that looks a lot like look at this equation. Well, wait a minute, look at it. Should there be an A there or an A prime? Well, here there's an A prime, and here there's an A. So the equations aren't the same, but they're closely related, and they're connected by something called duality. And the way duality, and this is duality exactly the same that you learn in your math classes, in the Lagrange multiplier theorem. They're linked by transposition and time reversal. And you know, this is a great insight due to Kalman and other people. And what it means is that there's an intimate connection between dynamic programming problems and filtering problems. And that connection, people that understood that connection, were able to formulate and solve a bunch of problems that seemed formidable and unconquerable by people who did not see the connection. So I'm not going to pursue that much more here, but it's a young assistant professor at Yale who has pursued it. So I think that's going to be enough for this lecture. Thank you.